So we're looking at volumes that are going to occur during inspiration and expiration. And these are going to be during resting breaths and then deeper breaths, right? You know, you can just take normal breaths and you can breathe really deep in and out. So remember, I already told you 500 milliliters is our tidal volume. That's the amount that we just breathe in and out at rest. So that's going to pop up here. There we go. Look at that tidal volume, VT. Of course, there's an abbreviation. There's also, you'll notice above that, a reserve volume. There's some amount of volume you have in reserve that's outside of that tidal volume. So anything outside of the tidal volume is going to be some sort of reserve. It's on reserve in case you need it. There's an inspiratory reserve volume. Up here, this would be, right, volume inhaled up this way. So right here is inspiratory reserve volume, the amount you can inspire by using those accessory muscles. And then tidal volume plus your inspiratory reserve volume is going to give you your inspiratory capacity, your total amount you can inspire. That's possible to inspire. It really is just equal to IRV plus TV, right? Sorry, that last one should be VT. We've also got an expiratory reserve volume. That's down there, kind of covered up. So raise this, ERV. That's the amount you can expire on top of what you do with your just resting breath. The total amount you can inspire and expire is your vital capacity, vital like alive. This is going to be your IRV plus tidal volume plus ERV. Yeah, this whole piece right here. But notice what is this green stuff down here? That is some stuff that you never can breathe out. There's some residual air in your lungs that can never be exhaled. And that's actually so that your lungs don't collapse. You need to have some air in there. Otherwise your alveoli literally are collapsed. So this is called the residual volume. That's what's down there. We can skip that one. The total lung capacity is all of these added together. That is an amount you never actually can breathe in and out without your lungs collapsing. But it is literally the volume that your lungs could potentially inhale and exhale. Here is another way of looking at that same thing. This is just a nice figure that I want you to have. You could label these different components going along this way. So here is tidal volume, those reserve volumes, and residual. You could add together those tidal volume with the inspiratory reserve volume, and you'd get inspiratory capacity. You could add all three of those together and get vital capacity. And this whole entire one here is your total lung capacity. With light exercise, tidal volume starts to increase, tidal volume continues to increase, and so does respiratory rate. So respiratory rate and tidal volume both, I should put volume tidal, both increase. This is also showing that someone who is trained actually taps into their reserve volume more quickly. That's effective training, partly to do with muscles. We're going to do some calculations of pulmonary ventilation. This is also called minute ventilation. So it's the amount of air that is inspired and expired per minute. Minute ventilation, that word really is what it is. So liters per minute. What do we need to know if we're going to calculate this? Similar idea to cardiac output. We need to know how many ventilations there are per how many breaths in a minute, and we need to know the volume of each of those breaths. So that's respiratory rate and tidal volume, or whatever the volume, tidal volume. So VE, that's pulmonary ventilation, it's equal to tidal volume in liters per breath times the frequency, so breathing rate in breaths per minute. Breaths cancel out, it's going to give you liters per minute. Very similar to cardiac output. So we can do an example here. We have someone who is taking tidal volumes of 0.45 liters per breath, 12 breaths a minute. Multiply those together, that's going to be a minute ventilation of 5.4 liters per minute. Great. So 5.4 liters are being exchanged each minute. That is a measure of how much respiration is occurring over that minute, opposed to in one single breath. So this is what's going to increase as you exercise, right? Both the breathing rate and the size of each breath, just like stroke volume and heart rate both increase to increase cardiac output. However, it's not going to be that simple, of course. So not all gas entering the respiratory system is going to participate in gas exchange. This is due to something called dead space. This is related to the anatomy of the conducting passages, basically the fact that they exist. So not all air that's brought in can exchange. There's a bunch of air in your bronchioles and trachea that don't get to exchange. So this is called dead space. So the amount of air that can actually participate in gas exchange is always less than what you actually breathe in and out. This is called anatomical dead space, and it's approximately 1/3 of tidal volume. So 1/3 of the air that's brought in and out is dead space. So about 0.15 liters in this scenario. So let's look at that. If we want to look at dead space, whoa, this looks crazy complicated. All we're doing here, though, is saying that alveolar ventilation, that's actually ventilation of the respiratory membrane, is our tidal volume minus our dead space. That makes sense. The amount of air that's actually going to participate in gas exchange, we're going to take out the part that doesn't participate in gas exchange. Is going to be always less than our tidal volume. Is about 1/3. We're still going to multiply by frequency. It's always going to be less than tidal volume. So alveolar ventilation, the actual amount exchanged each minute that participates in gas exchange, is going to be something like this. The dead space is about 1/3 of our tidal volume. So subtract that out. You also could just do in your head, right? That's 0.3 liters per breath. You maybe have already got to that participates in gas exchange, right? This is 0.3. 3 is not working. That's ugly 3. So alveolar ventilation is actually only 3.6 liters per minute.